Ladies and gentlemen, good afternoon. I'm more than happy to being here again here in Santos at the Offshore Conference. It's the third time now for me. For today, I'm going to present some studies on enhanced oil and gas production by the application of ultrasonic waves. Predominantly, these are the results of our studies we have carried out during the last 3 years in cooperation with a Swiss company. Actually, the Swiss company generously has funded us, which is most important for as a university, as you may know. Now, the application of ultrasonic waves is not new at all in our society. It's not new in our business, well known of over many, many decades. We are using the ultrasonic waves for the orientation worldwide, in nautics, for instance. We apply sonic waves for welding processes. We know application of sonic waves for density measurements, of course, for surface treatment. And of course, ultrasonic waves are well known in the industry for non-destructive material testing. So in other words, we don't destroy our samples if we apply this sort of tests. We are aware about the application in medicine, as to be seen here on the right-hand side. So everybody of yours, of course, has been confronted in the past, a few years ago, with the application of ultrasonic waves. And in our business, ultrasonic applications are to be seen in flow metering and in fumigation. But generally speaking, what is the application of ultrasonic waves nowadays in order to improve oil and gas production? What can we do in order to get more out of the ground in a more effective way and in a more cost-effective way too? Let me start with a few definitions and a few basics on ultrasonic waves we were supposed to understand before we go into the details of the worldwide applications. If we are talking about ultrasonic waves, we mean all those waves above 16,000 hertz. So a human being cannot hear this sort of waves. We, as a human being, I'm not saying that the nature doesn't hear more than 16,000 hertz. And we also need to understand, if we want to transport ultrasonic waves, we need incompressible media. So, for instance, if we are having a gaseous atmosphere, we wouldn't be able to transport these ultrasonic waves over a long distance, over a long way. So in other words, we need a liquid environment, since liquids, for instance water, are almost incompressible. I'm not saying that water is not compressible at all. This is not true. Water is compressible. This has a significant impact in reservoir engineering. But for our application, we can assume, and we can live with this assumption, that water is a sort of incompressible. And most important for this phenomenon is that we have to understand that at a certain point cavitation occurs. This means if we apply intensively ultrasonic waves, we generate some bubbles which may implode, and therefore extraordinary high pressure and temperature is generated at that time, and this phenomenon is basically used in our industry in order to apply the ultrasonic waves in an effective way. Now, if I are saying cavitation, what do we mean by cavitation, which is the driving motor actually for the ultrasonic wave application? And we mean by cavitation the formation and the immediate implosion of cavities in a liquid. This means we are forming small bubbles, they actually implode and then finally generate excessive energy, which is useful in our business. And it usually occurs when a liquid is subjected to rapid changes of pressures that cause the formation of cavities where the pressure is relatively low. In other words, there is an application given in every borehole worldwide, whatever the depth of the borehole is, and this phenomenon we need to apply at a later stage, and we will see what the benefit out of that is. The cavitation pimples implode, force which can be generated which are 1,000 times higher than the primary force which is exerted by the ultrasonic field and emitted into the media. And on the right hand side we see the formation of this bubble, and right at the stage of an implosion just before it's going to get imploded. And the most important for us is that we need to generate the cavitation. So cavitation is generated, or might be generated by ultrasonic waves maelstrom, and that's what we are going to use. Now, the focus thereby is that we are just applying limited energy by the ultrasonic field, and we generate 1,000 times larger force, which we can use then for different types of purposes. The question that arises now is how to generate basically ultrasonic waves. To dissipate electromagnetic oscillation, a force usually required which originates from the so-called reverse piezoelectric effect. And what is the piezoelectric effect all about? Just reducing it to the basics, all we are doing is we are forcing crystals in order to generate electricity. And if we are forcing crystals at the surface and the platelets together, then we can generate electricity, but this effect can be reversed too. This means if we apply electricity to the quartzite, for instance, then we can generate the forces. So it's reversible anyway as often as you want. And the piezoelectric effect is not new at all, well known since many, many decades. It's most important that this process is reversible in materials where we apply a mechanical pressure, here shown on the right-hand side. So as you may see, if we apply force at this sample of a quartzite, for instance, then electricity is produced. And the other way around, if we are applying electricity, then we are able to make this quartzite moving at a certain frequency. And this is the phenomenon we are using in the industry. How to use now these crystals? There are several ways well known throughout the entire industry. There are naturally occurring piezo crystals, and the most famous one, of course, is the quartzite. Well known because of these excellent and outstanding purposes, showing up at whatever the temperature might be, whatever the pressure might be in the surrounding environment. And you've seen there are several other types of crystals known in the industry. Some rare elements are involved here, and most expensive too, and this is the reason why the quartzite actually has most application worldwide. But besides from the naturally occurring crystals, we also know the man-made piezo crystals and also ceramics, a special type of a crystal. And we see here these different types, and I'm not going to plague you now with all these chemical formulas and all these different types of crystals and ceramic types. Anyway, they are most important nowadays because they're having unique behavior. They show up with unique behavior, and they are way better in sometimes than the conventional, than the natural quartzite, as we have discussed before. Some of the crystals also contain lead, and lead is questionable nowadays because of well-known environmental reasons. So the industry actually shows a strong tendency to keep off the hands from this lead-containing piezo ceramics and switching over to other alternatives. And alternatives are given; they are already in place. Being very honest, some of these solutions are more expensive than the conventional lead the lead piezo ceramics, but it is high of priority nowadays to apply this new technology in our industry. And finally, we also know that polymers are ideal to show this piezo effect. But even though we are here at a much less early stage of our research, we know that there is an application, but there is still room left for further research, what's to be done in the future. And I'm seeing lots of young people around here, and this will be maybe your future to work on this subject and to find out what's best of all for the solutions in our industry. Now let me step further. What are the key issues in our oil and gas business, and where can we finally apply these ultrasonic waves and make use of this phenomenon? And one of them is the degassing effect by ultrasonic waves. We all know, just think about a bottle of Coke, you may also think about a bottle of beer if you want, that gases are soluble in liquids. The gases are soluble in water, and gases are soluble in hydrocarbons in oil, for instance. Depending on the pressure and temperature boundary conditions, we can dissolve more or less. The higher the pressure, usually the more the solubility, the higher the solubility. And the higher the temperature, generally the lower the solubility. This applies for oil as well as for gas. Now back to the Coke sample. Put a bottle of Coke in the sunshine and open it, then I will see that you are going to have a hard time. If you take the bottle of Coke out from the fridge and open it then nothing is going to happen, or almost nothing. The point thereby is that the solubility for gas is going to decrease with higher temperature, and this is the reason why you are running in troubles if you open the bottle from the sunshine, and you are not having a problem at all if you take it out from a low temperature environment. We in the oil industry, we make use of that, and we need to get out these gas bubbles from oil, even so at low temperatures. And this means we don't need to apply extra energy in order to increase the temperature level, and we also can get out the gas from the liquid medias, from the liquid environment and lower temperature by the application of sonic waves. And we know, even though they are not visible from the very first stage, since they are finely dispersed in the fluids, might be water or oil, but if we use the effect of the maelstrom, these pimples might expand and coagulate to larger pimples then, and finally at the end of the day they are going, as discussed before, to implode, and then they can be recovered from the liquid phase. A very non-tricky operation, a low-cost operation at a low energy level, so highly attractive for our industry. What is the direct application? This is the degassing of oil and gas, from oil and water. And usually we are running these huge vessels of oil and gas separators or water and gas separators. But as we all know, energy is not for free. Energy is costly on one hand. And this huge constructions of a vessel limits our capacities, our offshore capacities, because space is one of the issues which is definitely rare in offshore operations. And finally, if we are talking about general drilling operation, we also know that gas which is penetrated, which is drilled downhole, is going to get dissolved in our liquid phase. We must understand that we are having high pressure downhole. Just giving you an example, in a deep well like 5,000 meters, we are having a pressure of at least 500 bar and more. If you just have a water column, it's 500 bar. And under this pressure and temperature conditions, the solubility for gas is given. What is the problem thereby? The higher the amount of gas dissolved in the liquid, the lower the density of the liquid column. On the other way around, if we enlighten our drilling fluid, then we don't have enough counter pressure to the formation, and there might be a so-called kick is going to happen. This means that liquids or gaseous medias are flowing into the wellbore and even further reducing the hydrostatic force of our liquid column, and the more gas or oil can flow into the oil. And what finally is going to happen, that's what we have seen on the first presentation this afternoon, the picture from the Gulf of Mexico. So a blowout is the final result out of that. What the engineers are doing and operators are doing at the surface, we need to remove the gas from the drilling fluid, from the drilling mud, and this is rather tricky since drilling fluids own parameters which are not allowing on a regular basis and at any pressure and temperature condition to remove the gas from the fluid. Again, there is an application for ultrasonic waves to get at a low energy level the gas out from the liquids. Another problem in our industry is that crude oil usually comes along in many areas of the world with paraffins and asphaltenes. Paraffins and asphaltenes are actually having the strong tendency to be deposited in the pipes. And they finally, because of this deposition, the inside diameter of the pipes is reduced. So we are creating a so-called flow restriction. We are hindering the natural flow all the way from downhole back to the surface. This means lower production, which is definitely unwanted in our operation. We want to produce as much as we can, being very honest with you. But the precipitations on paraffin and asphaltene is hindering this process. We know that we might remove paraffins and asphaltenes chemical-wise, but you have to get access, first of all, to this sort of deposition. There is no use of chemicals required in this particular case, and we have demonstrated in the lab and in the field that the application of sonic waves can reduce the precipitations of paraffins and asphaltenes. How is the removal process going to happen? Now, if this is our emitter, our ultrasonic emitter, we are sending waves directly into the reservoir. So we are lowering our ultrasonic tool downhole directly into the borehole, and at a certain point we stop, and then we start to emit this 30,000 hertz frequency into the reservoir rock. And if we enlarge this part of our reservoir sample, then we see the deposition here at that point, which hinders the flow of oil, which hinders the flow of gas. It could be debris or something else. And emitting these ultrasonic waves finally leads to the point that these porous throats, these pore channels, these tiny pore channels are clean again and allowing more inflow into the wellbore. More inflow into the wellbore means higher production, higher productivity of the entire process. What are the problems with wax precipitation? I already mentioned that the inside diameter is reduced. This is a field sample I brought for you here, and you can see that at the end of the day, finally, the entire volume of the diameter is plugged, and there is no more room left for any flow. So these pipes are definitely fully plugged. This ends up, first of all, in a lower production rate, and finally, in no more income, which is not that what we want to achieve in our business. Because of these precipitations, we also know higher frictions. So higher friction means that we need more energy to produce the fluid. This means more energy consumption, higher costs overall. And finally, also the surface facilities get plugged, and the pipelines too. And on the right-hand side, I brought a sample for you, what we did in the lab. Here on this left-hand side, we have a piece of a saccharode string. A saccharode string we need to pump the oil out of the ground by saccharodes. And this is fully adhering here and contaminated by paraffins. And after treating this sample in the lab with ultrasonic waves, we finally came up with the blank surface of the saccharode item, what we have tested. Here is the impact of the pressure losses by wax deposition, and on the vertical axis, on the y-axis, I'm showing the depth in thousands of meters, and here on the x-axis, I show the pressure loss in 100 psi. And I start on the right-hand side with a 1-inch diameter of a tubing size, and on the left-hand side, we get 3 inches of a tubing side. Now let's assume we are starting to produce a new well, and we have the full diameter of 3 inches, so we start here at that point with this sort of a pressure loss, and let's assume this is something like 1100 psi we are going to lose on the way up back to the surface in a depth of something like 10,000 feet, 3,000 meters or something like that. If now the tubing is gradually reduced in its inside diameter because of these precipitations of paraffins and asphaltenes, then we end up at a smaller inside diameter of 1 inch only, and see how much the pressure loss is now. It's more than 3,000 psi, so trifold as much as in the blank tubing as in the clean tubing. This means we are losing on the way up to the surface a hell of pressure. This means way more energy is consumed, and maybe the wellbore is not free-flowing at all. We have to implement artificial lift systems. And as I mentioned before, the worst case scenario could then be that the inside diameter is that small that the diameter is fully plugged and even no flow is going to happen. And this is a nightmare for every operator. Just before I left from Europe to Brazil, talked to my colleagues in the North Sea. They are in the situation now in a North Sea field, in a giant oil field actually, and they're having the problem of these precipitations. It's a shell-operated field, and they are having no production at all from some wellbores because exactly of this phenomenon. How was our setup in the lab at our university? Mentioned before, I'm cooperating with this Swiss company, Progress Ultrasonics, and they have supplied all these test devices. You see here the source of for the ultrasonic generator, and we are emitting via this type of a sonotrode here. So ultrasonic waves here just to the vertical downhole into this chamber. The trick thereby is that we have to identify the correct frequency, the correct wavelength, and how to emit an optimum to our object we want to get our hands on. And the trick thereby is the construction, the geometry of the sonotrodes. And another trick we are working right now on is which material we are going to implement. These are conventional high alloy steel sonotrodes, but in the future we are going to use ceramic sonotrodes as well. And I'm working with my colleagues from the Institute of Ceramics on this new type of sonotrodes for the next generation. This is just an vertical inflow performance presentation, how we can improve the productivity of our wellbore. And here on the, you can't see it, but I will explain it for you. You see the productivity of the wellbore on the x-axis, and we are seeing the pressure on the ordinate here. And the green line represents the inflow performance, and this means the lower the pressure, the lower the wellbore flowing pressure, the higher the productivity. And this is now the simulation of the large diameter without any presentation, and this would be the representative line with precipitations and with restricted inside diameters. And you see how much of a productivity we lose if we are reducing the inside diameter. So there is a substantial impact on our overall productivity of the wellbores, predominantly on oil production. I emphasize predominantly on oil production because we also know some gases or higher hydrocarbons which come along with paraffin and asphaltenes as well, causing the same problem. What are the reasons for other precipitations? These are not only paraffins and asphaltenes we are talking about. We are also talking about precipitations of calcium carbonate, for instance, and this precipitation they hurt in exactly the same way. They're even worse, because we are having precipitations which are not soluble. Calcium carbonate can be removed by the application of hydrochloric acid, but for instance, barium and strontium sulfate, the precipitations, they cannot be dissolved chemical-wise. They have to be removed in another way. One of the reasons might be the change of temperature. Well, pressure and temperature is changing on a regular basis in our lifetime of a field, so we cannot change this. We have to live with that. And another point which is very famous is supersaturation, so oversaturated media, for instance, and then this finally leads to the precipitation of salts. And another important point is the contact time. So this means the more we are producing, the longer the time elapsed in our production period, the higher the chance of precipitations. Now, what are further problems with scaling? It is not only the reduction of the diameter, of the inside diameter of our tubing string, it is also the problem that here, if this is our wellbore, that the precipitations in the near wellbore zone are well known to cause further pressure drops. And the higher the pressure loss in the near wellbore zone actually is, the lower finally the production rate will be. We are talking about, in this case, about the so-called skin factor, and we can to a certain extent remove the skin factors by applying acids to dissolve these precipitations, but this is not generally given. One of these options would be an interference between the application of ultrasonic waves and the application of HCl, hydrochloric acid, for instance. We don't know at the moment, and we have to be honest to ourselves. We have to go for further research. We don't know at the moment how deep our entrance could be into the wellbore and how high the energy must be, or what the optimum of the energy of our ultrasonic waves must be in order to get out an optimum of this stimulation. Another problem that might come along with the precipitations is this natural radioactivity. We know that our rocks are of a certain, some of our rocks in the industry, they own a certain amount of radioactivity, which is not a problem at all. But if over the years of production there is an accumulation of these precipitations, then it might be very likely that we exceed the maximum allowed amount of radioactivity, since radioactivity has accumulated. And then we are running into serious troubles. I mentioned before that we have carried out numerous lab tests over the last years. This is one point, but based upon the results of these lab tests, we also have carried out in the meantime field tests, and we started in the Gulf of Mexico. Another time was when we have to deal with the Gulf of Mexico, and we substantially could increase the productivity. And in this particular case, we could increase the productivity from 49 to 235 barrels per day. And in another case, we increased the production rate from almost 900 to 1900 barrels per day. Just by applying sonic waves in order to stimulate the wellbore. And the last results we have just got a few days before from Pemex, from the partner in Mexico, is that the last stimulation we carried out was 6 months ago, and we increased the productivity from 1400 barrels per day up to 2400 barrels per day. And the net income of what we finally made over this period of time, or the partner finally made over this period of time, is of a value of something like $14 million, which is quite substantial. Another application could be the deliquification of gas wells. This means if we are producing gas from our reservoirs, we are not only producing gas, but gas usually comes along with a certain amount of liquids. And if these liquids are accumulated at the very end of the wellbore and are not again by the stream, by the natural gas flow produced out from the hole, then the wellbore might die and there is no more production left. So all we are doing is we are trying to use the effect of the ultrasonic waves, as discussed before, to get fine, tiny bubbles and to accelerate the flow of the gas stream back to the surface. And all we need to achieve is that because of the Turner, the so-called Turner effect, we need to achieve a flow of this gas bubble which is higher and then the forces acting on the downwards on this liquid droplet. So this is the natural gravity acting on the droplet, and this is the drag force of the flow of the droplet, and this drag force must be higher than the gravity force downwards, and then the liquids are transported down back to the surface. So if we can manage that we can deliquify our gas wells, this means in the long term we get a higher production rate, and at the end of the day also a higher recovery factor. This means we can get out of the wellbore more than we ever could get with previous technologies, but with the permanent application of ultrasonic waves we even can increase the recovery factor. And we are all aware in our business that if we are talking about oil production, we have to live with the phenomenon that we are also producing water. And there must be found a solution what's to do with the water. We cannot spill it, so we have to find a solution, and the only one answer is to re-inject the water into the reservoir at another point via an injector where the water comes from. But the point that comes along thereby is rather tricky too. And this tricky point is we are having impurities in the water. In other words, we need to clean this re-injected water before we re-inject it, because otherwise we are creating further problems. One of these problems could be, for instance, that we are injecting bacteria, and bacteria which might generate in the future H2S, so sour gas. But for sure, our equipment is not designed to take sour gas, and corrosion coming along with H2S is well known. But the application of ultrasonic waves and ultraviolet light in combination has demonstrated that this could be a solution to clean the water up to a quality which is compares to drinking water. We are having this technology almost stolen, so to say, from the militaries, which have demonstrated already that they can transfer so-called black water, which is the water from the sewage system, from black water to drinking water. And exactly this technology is based on the ultrasonic waves and in combination with ultraviolet light. Another problem could be the creation or natural occurrence of bacteria downhole, and there's another application to get out and get rid of this bacteria problem and to kill these bacteria and remove them by the application of sonic waves too. You may have heard this unconventional gas resources, and you may have heard what gas hydrates are all about. Hydrates are huge resources worldwide, which are unknown actually in terms of their size. But the industry has demonstrated that there are huge unconventional energy resources left on the ground of the sea and in the permafrost area too. This is one point. But hydrates are also well known to be formed in our production system. This means little ice crystals are going to get formed, and they're going to get deposited in the system. Again, the same effect as with the paraffins and asphaltenes, they are going to plug our system. But we successfully could demonstrate that we can destroy ice, as to be shown here in the lab. We can destroy ice by the application of sonic waves, and our goal is, but we haven't applied this in the field so far, to even prevent the formation of ice crystals. The theory behind this, if we can destroy existing ice or hydrates, then if we permanently apply ultrasonic waves, then we also can manage to prevent the precipitation of ice crystals and the plugging of the system. Another interesting point what we could demonstrate is we can manipulate oil viscosities by ultrasonic waves. On the x-axis we show the timeline, and on the ordinates we show the viscosity in Pascal, millipascal seconds, and you see over the period of the time we substantially can decrease the viscosity from more than 30,000 millipascal seconds down to something like 1,000 Pascal seconds. What does that mean? Viscosity is actually the hindering factor in the natural flow of our reservoirs. The higher the viscosity, the more energy we lose, the more friction between the fluid and the wall of the tubings, and the lower the productivity. The other way around. If we can manage that we reduce the viscosity of these fluids, we definitely can increase the productivity of these wellbores to a great extent. And our final goal actually is to apply the sonic waves in the entire reservoir. Because if we can apply the sonic waves in the entire reservoir and at the same time reduce the viscosity in the reservoir, this means that we will increase the mobility of oil from the reservoir. And increasing the mobility of the oil from the reservoir finally means that we can increase the recovery factor. So we can get out more oil from the reservoir than we ever did before with conventional technologies. What we are doing in the field and what we have done and doing right now as well, we are just carrying out a few jobs in the Gulf of Mexico again. We are just lowering the sonor throats down to the zone of interest, here maybe to the perforations, and emitting the ultrasonic waves and stimulate the wellbore. How is the system set up? We just need a generator, of course, and the ultrasonic generator, and then we transfer the electricity down to the resonator here at that point, and depending on the setup, we can generate different wavelengths, different frequencies of a different intensity. We are limited, of course, in terms of intensity in the lab, otherwise we blew out our lab facilities, and this is definitely not that what we want to achieve. Here are a few pictures from the last job offshore Gulf of Mexico. You see here the device, which is centralized, well centralized in the borehole, and then lowered down, in this particular case, to a depth of 3,500 meters for stimulation. This is here on the left-hand side our apparatus from the lab, and our future plans are summarized here at that point. We know that in artificial lift we are having serious problems on these various types of artificial lift systems with precipitations, especially on electrical submersible pumps. This means because of the high rotational speed of the pumps, there is always a precipitation on these various components given. And applying permanently ultrasonic waves means that we can avoid these precipitations, and the mean time between failure, or the lifetime of the pump, in other words, could be extended to a non-defined day from today's point of view. And we also are going for cleaning the so-called gravel packs. Gravel packs are devices installed down in a borehole in order to prevent the sand production. Some of the reservoirs having a strong tendency to produce sand, and this sand finally erodes the system and finally plugs the wellbores too. But if the wellbore is plugged once, then there is no more production. Again, with the stimulation of these gravel packs we are going to carry out in a few weeks, we are improving the productivity again. And finally, I'm skipping some points now, we want to get our focus in drilling as well, so on the mud treatment too, the treatment of drilling fluids, in order to separate these various phases. Ladies and gentlemen, thank you very much for your attention.